This is a question from the acids and bases topic, 9 marks in total. It runs from A through to E. I'm going to recommend you pause on each section, try it, and once you've come up with your own answers, review with the remainder of the video. So here's part A, B, C and D, and finally part E. Okay, taking a look at part A, expression for Kw, you simply need to remember. It is a form of dissociation, and it's dissociation of water, but we're not including the water in the expression. The reason for this is that so little of the water dissociates that the concentration of water is so large we can assume it to be constant. So that's the assumption that we make. Now, the remainder of this question also relies on you knowing that expression for Kw. That's how important it is. Not just 1 mark in the multi-choice, but quite a lot of the 9 marks. And we'll see that with part B, where we want to know the pH of pure water at 10 degrees C. Answer to 2 decimal places. I'm using Kw, I'm going to write the expression out, and I'm bringing forward the Kw value that we were provided with. Now, I also need to make an assumption here. Any water molecule that dissociates will give 1 H plus and 1 OH minus. So we can be quite confident that in pure water, the concentration of H plus is equal to the concentration of OH minus. If that's the case, I can simplify the Kw expression. Kw is H plus squared. Rearranging that to make H plus the subject, I can now substitute the Kw value in. And this allows me to calculate the concentration of H plus, 5.41 by 10 to the minus 8 mol dm to the minus 3. I can now substitute that into my expression for pH, and that gives me a pH of 7.27. And is that a reasonable answer? It's close to 7, which is the pH of pure water at 298K, so I'd be happy to continue at that point. If I move on to part C, why is pure water at 10 degrees C not alkaline? Well, in a sense, we've already answered this by going through the previous question. Acidity and alkalinity are about the concentration of H plus and OH minus. So if they are equal, we don't have overall acidity and alkalinity. The pH might not be 7, but that's only true as a pH of pure water at 298K. That's the new idea we need to take on board in A level. Now, moving on to this calculation here, we've got the calculation of the pH of a strong base, calcium hydroxide. I'm still going to start with Kw. And I'm going to rearrange it to make H plus the subject. Now, when I look at my concentration of calcium hydroxide, I know that because it's a strong base, it fully dissociates. So my concentration of hydroxide is 0.0131 multiplied by 2. And to get that, you've got to remember that calcium hydroxide is CaOH2. There are 2 hydroxides within there. Now, when I put those figures in, it allows me to calculate my concentration of H+. I've got my concentration of H+. I can substitute that into my pH expression, and that allows me to calculate the pH to 12.95. Again, I'm asking myself, is that reasonable? It's a strong base, and it's 12.95 up towards the 14 upper limit. Absolutely. Happy to move on with that as well. Finally, part E. We've got the calcium hydroxide saturated solution added to a decimeter cubed of water and stirred the mixture until no more solid dissolved. Predict whether the pH of the magnesium hydroxide formed at 10 degrees C is larger than, smaller than, or the same as the pH of calcium hydroxide solution at 10 degrees C, and explain your answer. This is actually taking you to the group 2 topic from year 12. This is talking about the solubility of hydroxides. The answer is that magnesium hydroxide would have a lower pH. By that, what I mean is closer to 7. The reason for that is that magnesium hydroxide is less soluble. Remember, the solubility of hydroxides increases as you go down group 2. And if it's less soluble, that means less hydroxide ions, that means less basic.